Good afternoon, everyone, and welcome to today's webinar titled Introduction to Watershed Management Optimization Support Tool Version 3, known as WMOST. This webinar is sponsored by EPA's Water Modeling Workgroup. I am Dino Marshallonis with EPA, and I'll be moderating today's webinar. Thank you all for joining us. First, I'm going to briefly summarize some of the features of today's webinar. We hope everyone will have lots of questions for our speakers today, and you can type your questions in the questions box and click on the send icon. If you have any problems viewing the broadcast, just let us know in the same questions box, and we will post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Modeling Workgroup page, and we will provide that link for you on a slide at the end of the webinar. Also at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and will provide directions for downloading it at that time. Lastly, the materials in this webinar have been reviewed by EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of EPA. Mention of commercial enterprises, products, or publications does not mean that EPA endorses them. Now that we have covered the logistics, I would like to provide a quick introduction to the webinar series. I would like to remind everyone that this webinar is part of an ongoing series, and that the purpose of the series is to help water quality professionals better understand water quality modeling and how models can be used to solve the problems facing water quality regulators. Today is the 15th in our webinar series. All of the past webinars have been recorded and archived and posted to EPA's YouTube channel website. Links to the archived files are available on our Water Modeling Workgroup website, and the link is at the bottom of this slide. In a few weeks, an archive of today's webinar will be posted on the same website. Because this is a webinar series, we encourage you to go back and listen to some of those previous webinars if you haven't already. They do build upon one another, starting with modeling basics, and it moves up to the more advanced topics we're going to talk about today. These webinars are targeted at water quality professionals who may use, want to use, or review models as part of their job, but who do not necessarily have a modeling background. As such, we are assuming that you have a basic understanding of water quality science and concepts, but perhaps have limited direct modeling experience. And with that, I'd like to introduce today's speakers. Today's speakers are Drs. Naomi Dettenbeck and Amy Piscopo. Dr. Dettenbeck is an ecologist at US EPA's Office of Research and Development, Atlantic Ecology Division in Narragansett, Rhode Island. Her current research is focused on the watershed scale effects of natural and constructed green infrastructure, development of decision support tools for integrated water resources management, and development of EPA's estuary data mapper. Her past research has included work on biogeochemistry, wetlands, landscape ecology, nutrient criteria development, spatial statistical network modeling, and watershed classification. Dr. Dettenbeck earned her master's and PhD in ecology from the University of Minnesota. Dr. Amy Piscopo is an environmental engineer at the EPA's Office of Research Development, and her research there involves applying multi-objective optimization to different types of water resources management problems, including the implementation of green infrastructure at the watershed scale. Amy completed her master's and PhD at the University of Colorado in Boulder, where she researched methods to optimize remediation of contaminated groundwater. Her bachelor's is from Tufts University in Medford, Massachusetts. One last reminder, we'll have question and answer sessions at various points throughout today's presentation. We often receive more questions than we can actually answer. We will do our best to answer as many as we can, and we do have 2 or 3 of these sessions that I'll be moderating. Throughout the presentation, please type in your questions as you think of them, and we will get them periodically throughout the day. And with that, Amy and Naomi, I'll let you take it away.
So good afternoon and welcome. We're very happy to be talking to you about our latest version of WMOST, which just came out this past month, so this webinar is very timely, and also to discuss some of the upcoming features of and version of WMOST under development, which includes multi-objective optimization that Dr. Piscopo will be presenting. This webinar will be presented in 3 different sections. The first section will include an overview of concepts related to integrated water management and optimization, and then an overview of WMOST. I'll focus mostly on the hydrology module, stormwater BMP module, and combined sewer overflow module, as these are the latest features in version 3, and finish up with a brief discussion of the optimization process. We'll have a brief question and answer, and then move on to part 2, where I'll discuss 2 different case studies applying WMOST version 3, one in Cabot Creek, Maryland, and the second in the Upper Taunton River in Massachusetts. Have another question and answer session, and then finish off with part 3 with Dr. Piscopo talking about multi-objective optimization, and finishing up with a discussion of future directions and additional available resources. Okay, so we developed WMOST to facilitate integrated water resources management by communities and watershed organizations. So why is integrated water resources management important? We know that cities are facing significant challenges with respect to sustainable water use, which deals with both quality and quantity issues, and also cost-effective management. Integrated water management is one solution to these challenges. It consists of system-level approaches that try to achieve a balance between social, environmental, and economic outcomes. As a systems-level approach, it requires high levels of collaboration between specialized departments that may normally be stovepipes. These include wastewater, stormwater, drinking water, and even land use planning. And as such, IWRM supports the one water concept, that is viewing wastewater, stormwater, groundwater, or other water sources as interconnected parts of the same resource. To introduce some of the key concepts of optimization, I'll walk through a simple problem in integrated water management. So let's consider a case where our goal is to determine the least expensive changes to infrastructure to prevent groundwater depletion. So in this case, we have 2 goals. One is preventing groundwater depletion, and the second is minimizing cost. We'll consider a number of different decision variables related to changes to infrastructure, including repairing a certain percentage of leaks in wastewater pipes, reducing withdrawals via a price increase, and infiltrating stormwater with best management practices from a certain land area. Some of you may be familiar with using simulation models to play what-if games. And so I'll start out with an example of how you would do this in a simulation mode. Again, we have the goals outlined here. We might start out with a simple scenario where we just look at repairing all of the leaks in the wastewater pipes and come up with an associated cost and find that we're still depleting groundwater. And then work through other scenarios with different combinations of our decision variables. So the second one has a greater cost, we're still depleting groundwater too much. Look at another option, even greater cost, but now we've met our groundwater depletion goals. Or we might have gone too far in this case, so we might back off a little bit. Want to see if we can still reduce cost a little bit. And ultimately end up with scenario 6. However, at this point, even though we've gone through 6 scenarios, we still don't know if we've gotten to the best solution for this problem. And this is a fairly simple problem, but you can imagine if we dealt with a more complex problem and we're dealing with endpoints at a daily time step, that you might end up going through hundreds, if not thousands, of simulations to come up with an answer. In contrast, if we solve this problem using optimization, again, we'd have the same set of decision variables, but now we would start out by setting these up as constraints with permissible ranges. So 0 to 100% repair of infiltration, leakage, X% price increase between 0 and 20%, certain range of design volumes for stormwater BMPs, and areas on which to implement those. In this case, we could solve the problem with one optimization routine and come up with the least cost solution to achieve our goals. So it's a lot more efficient doing it this way. This also shows you the basic features of an optimization problem. You have a series of decision variables, an objective. In the case of WMOST, we deal with a single objective that is minimizing cost, and we deal with our other targets as constraints. So what does WMOST do overall? You can think of it as an accounting system for water and pollutant loads at the watershed scale. It's designed to work at the HUC 12 to HUC 10 scale, so maybe 10,000 to 40,000 hectares. It allows the user to identify water-related goals and constraints, and then evaluate integrated management practices, looking across stormwater, drinking water, wastewater, and land conservation practices, and ultimately using optimization to minimize the cost of solutions to meet the targets of concern. I also should have mentioned that although it's designed to work at the watershed scale, you can apply it at a portion of a watershed, say if you wanted to use community boundaries, and then you would just need to define the inputs and the outputs from that unit. WMOST is built on an Excel interface. It's designed to be compatible with version 2016, but it's also backward compatible to 2013 and 2010. As you can see, the spreadsheet provides embedded instructions and different buttons to push to take you to different spreadsheets within this and to start different modules within the tool. So you start out by choosing the type of module. You can run just the hydrology portion or look at both hydrology and pollutant loads. You then proceed to a series of data input screens. I'll show you some examples as we go along. Then you start the optimization module, and finally you get to review results in a series of tables and graphs. And again, we'll show you some examples later on. So we designed WMOST to meet the needs of community decision makers and also watershed managers. This could include utility managers, municipal planners, consultants, communities, and others. It's designed to inform planning level assessments, and here are just a few of the potential applications. So it can be used to provide supporting information for loans and grants. Even FEMA now has mitigation grants that can support the implementation of green infrastructure, so that's one potential use. It can be used for long-range planning, for example, dealing with CSO problems or long-range plans for utilities. It can be used to support watershed implementation plans to meet targets for load reductions for TMDLs, or to support integrated plans to meet wastewater and stormwater permit requirements. The general process is outlined here. You start out with identifying your area of interest and the issues of concern, determine the goals, constraints, and timeline. You can either look at current conditions with respect to land use and climate, or look at future scenarios with respect to development and climate change. You decide which management options you want to consider. We have a wide range of management options included in WMOST. However, you don't have to turn these all on at once. You can use it to solve a very simple problem or a very complex problem. You have to compile a certain amount of data to run WMOST. One of the main inputs are time series for weather, hydrology, and pollutant loads that are derived from watershed models that are run outside of WMOST. We do have a data library of pre-processed watershed model output that you can use as a starting point, and I'll discuss other sources in a little bit. You typically need to provide some information on existing infrastructure capacity and associated costs if you want to upgrade that or change the capacity. If you're dealing with a water supply issue, you need information on water demand and withdrawals. We do have a flooding module within WMOST, so if you're interested in that, you need enough information to populate a flooding cost curve for different flood return intervals, and that could be generated, for example, using FEMA's HABUS tool. We have options for calibrating WMOST, and finally evaluating the optimal solutions and trade-offs. These are just some examples of the kinds of questions you can ask with WMOST and the kind of decision variables you might want to consider. I'll just walk through two of these as an example. So if you want to maintain base loads in a river, both to support fish communities and reduce effluent impacts at low flows, you might want to consider price increases or water conservation incentives, repairing leaks, implementing green infrastructure to increase infiltration, or reducing interbasin transfers of water. Conversely, you may be interested in water quality targets and reducing excess nutrient loads to meet water quality criteria or TMDLs, and also reducing or eliminating sewer overflows. And there you might want to look at a combination of land conservation, stormwater BMPs, riparian buffers, and upgrades to septic or wastewater treatment. WMOST represents both natural and anthropogenic features of the water system, and I'll walk through a flow diagram here. With respect to source water, the water obviously comes in as precipitation and then is partitioned as runoff versus recharge into surface water and groundwater respectively. It is a simplified model, so it's representing a single reach within the watershed and optionally a reservoir at the base of that reach. You can also represent external withdrawals and discharges to surface water or groundwater. You can represent water treatment for drinking water for the potable system, as well as interbasin transfers if the water is treated outside of the watershed. WMOST has the option of considering both potable and non-potable distribution systems and accounting for consumptive uses. You can represent both septic systems and wastewater treatment plant, as well as interbasin transfer if the water is treated outside of the watershed or the study unit boundaries. And then finally, you can consider options for water reuse and aquifer storage and recovery. So within this flow diagram, there are a variety of options for implementing management changes. You can look at conservation of undeveloped land, implement stormwater BMPs, either traditional or green infrastructure, change your reservoir operations, optimize operations or change the capacity of the drinking water plant, repair leakage, look at reuse options with non-potable water, manage demand through incentives or price changes, reduce infiltration and inflow, increase capacity or upgrade the wastewater treatment plant, provide additional treatment for reuse through a water reuse facility, or look at options such as flood skimming with the ASR. And finally, you can look at changes in interbasin transfers, either for drinking water or wastewater. These are some of the new features in WMOST version 3. Versions 1 and 2 only dealt with water quantity targets, so things like base flow, peak flows, and water storage. We now have improved data import options. We have developed a preprocessor that allows users to format existing model output from SWOT or HSPF for WMOST input. We have developed an automated way to import preprocessed model outputs via a web link within WMOST. You can also interactively explore those preprocessed data within our S-Story Data Mapper application. WMOST version 3 now contains a water quality module, enabling you to look at point source and non-point source loads, as well as septic and wastewater treatment plant effluents. We have an expanded set of stormwater BMPs, including both structural and non-structural features, as well as a few agricultural BMPs built in. I'll provide some examples later. We include some non-structural BMPs such as street sweeping as well. We've expanded the infrastructure module to include the septic and wastewater treatment plant systems and added a combined sewer overflow module. This is the same diagram I showed you previously. However, here I've added the sewer system so you can see where the combined sewer overflow module modifies the system. So the runoff can be routed either to a combined sewer or a storm sewer, or split between the two for different portions of land use within the watershed. The wastewater is routed either to the combined sewer or a sanitary sewer, or a combination of these, and from there it can go to offline storage as one potential treatment option during high flow events before going back to the wastewater treatment plant. This graphic shows the overall flow of information into and out of WMOST and how WMOST can interact with other models. So I mentioned the preprocessor, which formats watershed model output to produce the time series that WMOST needs. I mentioned we have the output available on the server for automated import or available for Explorer in S-Story Data Mapper. The time series that are needed are runoff, recharge, and pollutant loads, as well as the weather time series. And these are organized by hydrologic response unit, or a combination of land use and soil type. WMOST interacts with EPA's sustain tool behind the scenes in the stormwater module, and basically this adjusts the time series for BMP processes, accounting for reductions in runoff, increases in recharge, and reductions in pollutant loads. If you're using the flood module, you can create outputs from HAZUS and import those into WMOST. Once you have the problem set up in WMOST and have run the optimization, start of the optimization module, you generate output files that are uploaded to the NEO server, which provides online optimization programs. The output from that is then imported back into WMOST to go to the results tab and displayed in a series of tables and graphs. So for the next several slides, you'll see different portions of this flow diagram highlighted so you can see where we are in the process. So we'll start out looking at the land use and hydrology module. So we're over at the left-hand side of the diagram that we started with. And basically, an HRU, again, is a unique combination of soil type and land use. So each of these, when the precipitation comes in, it's split between the runoff and recharge time series. So it would be a series for each of these unique combinations of land use and soil type. The input databases for baseline conditions, there are 2 to 3 data sets for Watershed, including Watershed characteristics file, which includes the descriptions of the hydrologic response units with associated effective impervious areas, infiltration rates, and groundwater recession coefficients. For each HRU, you have a time series of runoff and recharge for both water quantity and water quality. Currently, we can handle nitrogen, phosphorus, suspended sediment, and zinc. The weather time series, and then a recharge adjustment time series. Watershed models can sometimes generate estimates of negative recharge if the evapotranspiration exceeds the available water. So what we do is change those to zeros in the input data set to avoid problems in the optimization program, but then adjust for those later in another time series. And all of that's outlined in the user guide. The map on the right shows a subset of the watershed models that we have pre-processed and available for input. I mentioned the hydro processor. This is a standalone tool. Basically just formats the time series for WMOST. Right now it handles output from HSPF and 2 different versions of SWAT. The 2012 version of SWAT is the one that's used by EPA's HAWKS application, which allows users to set up SWAT models at the HUC 10 or HUC 12 scale across the country. We have the ability to interactively visualize and download data via EPA's estuary data mapper. There's a screenshot of that on the bottom. I'm also showing a screenshot of the data import portion of WMOST on the top, where you import data via a REST query, and I'll give you a demonstration of that in a minute. So in the estuary data mapper, you start out by zooming into your area of interest. On the Get Data tab, you choose WMOST and the endpoints and HUC 10 or HUC 12 of interest. You can then display that. Here I'm showing the hydrologic response unit with the land use and soil classes for a particular HUC. And then you can save the data. You can save a series of shape files and CSV files with a time series and import those into WMOST. There are other sources for output from calibrated watershed models. I mentioned EPA's HAWKS system, which came out within the last year. It provides an interface for parameterizing SWAT models nationwide. It also includes an access to future climate scenarios. EPA Basins, which many of you may be familiar with, includes a utility called HSPF PARM, which includes a database of parameters from existing calibrated HSPF models with associated metadata. So you can set up you can rerun somebody else's HSPF model, basically. Then there are 2 repositories for SWAT models, HydroShare, developed by Quasi, and something called SWATShare. And in the future, EPA has been working on something called the Watershed and Economic Data Interoperability System, which will provide another data archive for watershed model output. So now I'll walk you through the process for importing information from watershed files. So we moved from the first page of WMOST to the input data screen, And we're starting in the top, the baseline hydrology module section. So when you open up WMOST, this is the first screen that you see. You can put in a name for your study area, choose between hydrology or hydrology and loadings, and then proceed to input data. You choose the constituent that you're interested in. In this case, I'm going to be looking at total phosphorus. And on the left-hand side, these are the automated options. You can also manually input data from your own model using the options on the right-hand side here. So I'm going to go into the baseline hydrology module. You start out by letting WMOST know where you've stored the database inventory file. And that is downloaded from the WMOST website. I've already filled in the next options, so you enter the name of the watershed, the model type. We have swim model output, SWOT, and HSPF. Land use scenario, we have historic model runs from the 1990s and 2000s, as well as in some cases some future scenarios going into the 2100s. For climate scenarios, you can either look at historic conditions with a baseline feature, or for some models we have output from different climate change scenarios included. And then finally, the HUC 10 or HUC 12 for your subbasin of interest. We do have some PDF maps of various watershed models on the website as well to help you zeroing in on your subbasin of interest. So at this point, you retrieve the characteristics and weather data. It's pulling these in over the internet, so you need an internet connection at this point if you're using the automated feature from our server in RTP. So at this point, it's downloading all of the HRU and weather data, and it will subset that in a subsequent set based on the selections that you make. And you can see that it's populated the table below. Whoops, I interrupted it, sorry. It's populated the data below with the different hydrologic response unit types, including a code and a description. The model may include more HRU types than are present in your particular subbasin. So in this case, to provide a simple example, I've just placed X's by the top 6 hydrologic response unit types for this example. So we're looking at forest, different densities of residential land use, and agriculture on sand and gravel. This always takes longer when you're doing it for a group. I think what I may do is go back to the slides and come back to this in a minute once it's finished to show you the output. Okay, so when you import the data for the time series, you're accounting for non-point sources. You may also want to account for point sources in the watershed. You get to there from the data input screen, item 4, water supply sources and infrastructure. You go to the surface water and system targets, and that leads you to this page. I'm zooming into a portion of that. Here you can put in loading time series. The first 2 columns are for surface water and reservoir loadings. These account for point sources other than the wastewater treatment plant, which is accounted for separately. And then you can account for external surface water loadings. This includes upstream inputs if the headwaters are not included in your system. You can do the same thing for groundwater with a time series for point sources other than wastewater treatment plant, effluent, and septic effluent, which are dealt with elsewhere. and also account for external groundwater loadings. Okay. So I'm going to go back to WMOST and then continue the demo with the stormwater BMP module. Hopefully this is finished while I've been, yes. So you can see the HRU table has been populated. I've pre-selected these first 6 HRUs. And I press the populate land use area. That just pulls in the HRUs of interest and creates a table with the associated characteristics. So now we're in the land use tab. We have a list of selected HRUs, the area of each of those in the HUC of interest, the associated percent impervious area and infiltration rate. This is also where you could identify a range of areas for applying land conservation with associated costs and annual maintenance costs if applicable. So we're going to go back to baseline hydrology. And I've selected the time period of interest. You actually get the whole range of precipitation data. You can press this load precipitation data at this point and look at the time series if you want, calculate statistics and look at graphs, and choose some representative wet or dry years of interest. I've just chosen one growing season for 2006, which was a relatively wet year. You choose whether you want to look at a daily or a monthly time step. You'd want to look at a daily time step if you're considering stormwater management or flooding. Monthly would be appropriate for a lot of water supply problems. We now want to retrieve the time series data and populate it. So it's downloading the data, including all of the loading time series, putting them in, putting the zip files into a directory on your computer and unzipping those. I'll show you what those look like in a second. And setting up the input time series for runoff, recharge, and loadings. Okay, so now we can look, we have the runoff, recharge, and loadings tabs. For each of these, you have a different time series for each hydrologic response unit for baseline conditions. I'm going to go back to the input screen and move to the stormwater hydrology module now. You choose whether you start out with a baseline hydrology module or enter your own data. Import the hourly time series. Again, specify whether you want the daily or monthly model, and then choose the BMPs of interest. There are drop-down lists to choose different stormwater BMPs. I'm just going to look at a bioretention basin with a design depth of 1 inch. We have default data in here for first order loss rates. You can override those if you have more appropriate local data. This page also has other options to describe agricultural BMPs. I'm not going to go through those in detail today, but there's plenty of information in the user guide on those. So we're going to generate the input files for the stormwater model. This is generating input files for EPA Sustain tool. You do need to install Sustain on your computer, but you don't need to know how to run it. WMOST is taking care of that for you. So you can see it's generating the files for each hydrologic response unit. And now we're ready to run Sustain. And you can see that for this simple example, it's running fairly quickly. It's just processing the output files now. So at this point, for each of the tabs, runoff, recharge, and the loading tabs, we have both the baseline time series for each hydrologic response unit and one managed HRU set for each BMP of interest and each HRU combination. complete list of the BMPs included in WMOST. For stormwater control measures, we have both structural and non-structural, including both gray and green infrastructure options. We also include some alternative practices such as stream bank restoration and outfall enhancement. Non-structural practices include street sweeping, tree canopy, and urban nutrient management. We can model riparian buffers and also a handful of agricultural best management practices. So when you set up the management options for the BMPs, you choose the BMPs of interest, the design depth, and the loss rates. Again, you can import default loss rates or override those with your own. And at that point, WMOST creates a table for each BMP with the description of the HRU. You can choose the minimum and maximum areas for application. We do have default costs for capital costs and annual operation and maintenance costs. You can override those if you wish. And I showed you in the example how you're converting the baseline time series to the managed runoff, recharge, and loading time series. And I've already went through the demo. You may also want to consider upgrades to septic and sewer systems. Those are under item 3 in the data input slide section under septic and sewer systems. You put in information on the daily average effluent concentration for normal septic systems. We have some default data available, or you can override that. And then if you want to look at enhanced septic systems, you can put in concentrations and costs and capacity associated with that option. On the data input slide, you can also get to the CSO module. These are some extracts from that page. So you can specify a maximum number of CSO events per year you want to tolerate, as well as the capacity for runoff routed through the combined sewer and the capacity for sewage flows to the wastewater treatment plant. You have 2 different options for managing CSOs. On this page, offline storage and also sewer separation. And here you also specify the area that's serviced by the combined sewer system. There are also a number of features you can explore in the infrastructure module. I'm not showing you the whole page here, but this is the basic kind of information included in the infrastructure module. You can put in a planning horizon and an interest rate. You also have options to explore to provide information on capacity and lifetime of remaining or new construction, associated costs, both capital costs and annual operation and maintenance costs, for increasing capacity, upgrades, or repairs. So this includes information on water services, pumping, a water treatment plant, repairing leaks, wastewater treatment plant, the water reuse facility, and aquifer storage and recovery. So at this point, you've accounted for point and non-point sources and chosen various management options. Now you can choose what constraints you want to set. You can set flow constraints or water quality constraints. Here I'm showing you in the surface water tab where you set the target concentration or target loading values. And the -9 is in here as a default. If you don't want to consider those, you just put in -9, and WMOST ignores that as a potential constraint. So at this point, we've put in the input data, we've chosen our management options of interest, and chosen our constraints, and we're ready to start the optimization program from the first page. What WMOST is doing behind the scenes is using, in VBA code, it's producing another series of code written in AMPL, a modeling language for mathematical programming. And this simply sets up the optimization program. So you can see some example equations at the bottom. The first one describes the cost objective. You want to minimize cost over all those different management options. And then it lists a series of equations describing your constraints. So the first one listed there is simply describing annual runoff, total runoff, broken out by land use type and area. At this point, you're ready to upload the optimization program files to the NEO server. WMOST uses the BoneMin solver on this server. The server actually has a wide range of different solvers available. BoneMin is a mixed integer and nonlinear programming solver. In versions 1 and 2 of WMOST, we had a linear programming solver that you could just download, LP-solve. But with the addition of water quality, we had to go to nonlinear solutions. And you can choose between two different algorithms. The hybrid algorithm is the default. It tends to be quicker, but you can also try the branch and bound algorithm. There's a discussion of that in the user guide. If it's a simple problem, it will run right away on the NEO server. Otherwise, you'll be sent an email when your job completes, depending on what other people have jobs queued in line. This is what some example output looks like. You simply cut and paste from your computer screen to a word processor like Notepad, save it as a text file for import to WMOST. So there's some information at the top that WMOST doesn't use about the optimization run, and then that's followed by a list of the final decision variables at the bottom. And at this point, WMOST packages that in the results module into a series of tables and graphs. So there are 4 different kinds of outputs. The main one of interest is usually the summary table, which lists the management practices to meet with the least cost solutions. So the management practice level of implementation and associated costs to meet the goals. You can also look at the time series table of flow loadings and concentrations following the optimization, as well as graphs displaying those. You can compare the modeled stream flow and base flow or concentration or loads with measured values as part of a calibration process, or you can compare the modeled values with the target values to see how well you've met your goals over the time span of interest. WMOST also produces a scenario log file that contains both the input data and the results for analysis that can be used later with a tool called SendCompare, which we don't have on the website yet, but which will be available over the next few months. SendCompare allows easy comparison of results from multiple runs of WMOST. So, for example, you might want to look at the results of different climate change scenarios and see how your management options and costs differ. For that, we're ready to go to questions on part 1 of the webinar.
All right, thank you, Naomi. I'm just going to pause here for a little bit to let some additional people get their questions typed in. And just a reminder to folks to keep typing questions as you think of them. And if your question doesn't get asked today, or if you'd like to contact the speakers directly, their contact information will be on a slide presented at the end of today's webinar. So now let's just go to a couple questions. We have a whole bunch that have come in. The first one is, are there any specific requirements for time step or time interval for the flow that you use in the model?
As I said, WMOST can be run either on a daily or a monthly time step. We're actually ingesting watershed model output from an hourly time step for the stormwater module, but then the optimization is running on either the daily or the monthly time step. And I believe Sustain, if you put in a daily time step, it will convert that to an hourly time series.
Okay, great. We have another question about getting access to HRU data for input. Does WMOST handle other HRUs, for example, from the West Coast areas?
We don't currently have pre-processed data for any of the Western watershed models, but I did provide you with a list of sources, and you can also use Hawks to generate a SWAT model for any portion of the U.S.
Okay. I think you might have touched on this, but just we'll go over it. Can WMOST represent input of alternative sources of bulk water, such as from a desalination plant?
Yes, you should be able to handle that with your input time series.
Okay. And then can you use the model to relate back to aquatic life impairments from in-stream habitat loss, entrenchment, or loss of connection to floodplains?
You would need to identify flow targets that corresponded to the aquatic life uses that you needed to protect. So you need to have relationships between flow, minimum flows or peak flows to the aquatic life use endpoints of interest.
Okay. Can a dam removal be entered in as a management option?
We haven't tried that one. You might be able to do that under reservoir operations. If you want to send me a follow-up email, I can think about that a bit and get back to you with a more detailed answer.
Okay. Does the output file from SWOT or SWIM need to be edited before it's ready to be used by WMOST?
Yes, that's what the hydro processor does. It formats it for use in WMOST. There aren't many changes that are needed, but we take care of the formatting within the hydro processor tool.
Okay. Here's a good one. How accurate is this program, and is there a report that lists uncertainty of the results?
That's a good question, and the accuracy will depend on a number of factors, including how good the watershed model is that you use to populate WMOST and the other input data that you put into the system. We do have a calibration module, which includes the ability to look at different calibration statistics like the Nash-Sutcliffe coefficient. And you can also do uncertainty analyses, essentially sensitivity analyses by varying different input parameters and see how they change the results.
Okay, here's a question. Does WMOST calculate the energy used or the used energy for each scenario?
We don't currently track energy usage. No, that would certainly be a nice addition for the future, but we're not at that point of sophistication yet.
Okay, and then what is the typical solution time for an average system, such as the example described in the presentation? I think they're trying to get at what's the typical run time for the program? Okay.
It can vary anywhere. I was generating, well, it can vary anywhere from a few minutes to up to 6 hours. And sometimes you do have to wait for the output file to be returned from the NEO server.
Okay. And then we have a bunch of questions related to sustain and the WMOST sustain interface. The question is, so WMOST prepares the data and runs sustain in the background inside of the spreadsheet, and does it display the results in a location where they could be seen within the spreadsheet as well?
Yes, and that's what I was showing with the managed time series. So it's showing the modifications to the runoff, recharge, and loading time series that result from the application of the stormwater BMP module, which is using sustain. I believe, I'm not sure if they're asking if the sustain files are saved in the directory. I think that's only temporary, so I'm not sure you can actually look at those.
Okay. We have more material to cover, and there's still some questions, but I think I might save them for a little bit later because I don't want to miss any of the content of your presentation. I would just encourage everybody on the web to continue to type in questions, and we'll try to answer them at the end of the presentation. And with that, I think we're going to switch it back to Naomi and Amy. Thank you, guys.
Thank you. All very good questions, so keep them coming. So in the second part, I'm going to walk through 2 case studies. We'll start out looking at a portion of the Chesapeake Bay, and here the challenge is to reduce pollutant loads to the Chesapeake Bay system. Many of you are probably familiar with the total maximum daily load for Chesapeake Bay, which requires reductions in nitrogen, phosphorus, and sediment loads. If you look at the bar graph on the left, you can see the loads partitioned to different sources: agriculture, urban runoff, wastewater, and septic. You can see that prior to 2015, most of the load reductions were actually achieved via wastewater controls. However, in subsequent years, more and more of the load reductions have been assigned to urban runoff. So if you look at the Stage 2 watershed implementation plans, 24% of the nitrogen and 36% of the phosphorus planned load reductions are supposed to be generated through stormwater controls. So this first case study is looking at the Cap John Creek in Maryland, which is a highly urbanized subwatershed to the Potomac River, which is a tributary, again, to the Chesapeake Bay system. This is a case study being done in conjunction with the Maryland Department of the Environment, Montgomery County, and the city of Rockville. And here the challenge is to identify the most cost-effective suite of stormwater BMPs in this highly urbanized watershed to meet both the nitrogen, phosphorus, and sediment targets for the downstream Chesapeake Bay TMDL, as well as a local TMDL for sediment within the Cap John Creek. In working with Maryland Department of the Environment in this case study, they're interested not only in providing solutions for this watershed, but also using the results to provide guidance to other communities facing similar challenges. So here the objective is to minimize costs between the period 2014 and 2025, including both capital and annual operation and maintenance costs. We're looking at a variety of management options, including stormwater BMPs, forested riparian buffers, and non-structural BMPs, as well as the alternate BMPs that I mentioned before. With respect to constraints, we're dealing with the reductions in loads to meet the Chesapeake Bay TMDL, as well as a 23% reduction in suspended sediment load for the local TMDL. This example is somewhat simplified in that we don't have to deal with water supply or wastewater constraints because of the interbasin transfers for drinking water supply and wastewater treatment that essentially balance out. So the sources and treatments are both outside of the watershed. In this case, we derived our input time series from the Chesapeake Bay watershed model. We had to do a little bit of additional pre-processing because they had the output lumped by soil type, and we wanted to look at differences between different soil groups. So we split those between soil groups A, B, and C, D. And then we created blended pervious and impervious HRUs. So that provided information to populate the hydrologic response unit characteristics table, the time series of runoff recharge, and pollutant loads. This is an example of a portion of the results table that you see. First, I'm showing you the pre-optimization 2014 costs based on the application of existing BMPs in the watershed. So you can see that there are 2 different types of BMPs that predominate, almost equally applied: gray infrastructure in the form of dry detention basins, and then green infrastructure in the form of wet ponds. We did a run comparing a wide range of stormwater BMP options, including both gray and green infrastructure types. And after optimization, the only BMP that was chosen to increase as the least cost solution were the wet ponds. And you can see a substantial increase in the number of acres treated in this run. And here the goal was to reduce nitrogen loads by 5% from 2014 base conditions. WMOST also produces graphical output. Here I've actually superimposed 3 different runs. Baseline conditions shown in dark blue, An optimization run just looking at green infrastructure stormwater BMPs in orange, and an optimization run just looking at riparian buffer solutions. In all cases, we could achieve the 5% annual load reduction. I've summarized the results for cumulative cost and implementation acres for each of these scenarios. One of the nice things you can do with WMOST is to compare wet versus dry year inputs to see how robust the solutions are across a varying weather regime. So here we're comparing solutions for a relatively wet year, 2003, versus 2014, which is relatively dry but had one large event. When we looked at stormwater BMPs, wet ponds were chosen as the lowest cost stormwater control. However, the riparian buffers provided a lower cost solution for a 5% annual nitrogen load reduction, but obviously had much smaller runoff volume benefits. So in summary, for this particular case study, the previous implementation had favored a combination of dry detention ponds and wet ponds. For nitrogen load reductions, we found that wet ponds would be the most cost-effective solution, looking at green infrastructure, with riparian buffer restoration as an alternative lower-cost option. However, for total suspended solids, where there was a much higher target load reduction, riparian buffers alone could not meet the 21% load reduction target for the wet year, but a combination of wet ponds and forested buffers would be needed. Not surprisingly, the required levels of implementation varied across wet and dry years. We also found that the annual load reduction target didn't necessarily meet the maximum daily load target, so those had to be considered separately. As in most case studies, this is an iterative process. Having seen the initial set of outputs from WMOST, Montgomery County and the other stakeholders in Maryland Department of Environment are interested in exploring additional questions, refining the maximum number of acres to be treated, comparing the effectiveness and cost of non-structural and other alternative BMPs, evaluating dry detention pond conversions to green infrastructure, and also looking at adding base flow and peak flow constraints. And as I mentioned before, Maryland is using the results of this case study to provide guidance for similar communities and watersheds dealing with similar targets. And the bottom is just a quotation from Maryland Department of Environment Secretary outlining the challenges they're facing in meeting stormwater permit and TMDL restoration requirements in a cost-effective fashion, and the benefits of using a tool like this. In the second case study, we're looking at moving to New England. Here we're interested in informing community planning decisions in watersheds that still have some outstanding natural resources to protect but are experiencing rapid growth. So we're looking at the Upper Taunton River in southeastern Massachusetts. You can see the map on the left shows a portion of the Upper Taunton that has been designated as a wild scenic river. At the same time, this watershed is the second fastest developing watershed within Massachusetts, with attendant growing pains. The photo on the right shows some algal scum floating on the top of main stem portion of the Taunton during a relatively dry year. EPA Region 1 provided funding in the form of a Healthy Communities grant to a consortium in southeastern Massachusetts interested in working on this problem, which included both local planning agencies, the Southeastern Regional Planning and Economic Development District, and the Metropolitan Area Planning Council. Those planning agencies provide support for communities in the region. There were also a number of NGOs involved, Mass Audubon, Manomet, and the Nature Conservancy. Here, there are two different phases to the optimization problem. In the first part, we're interested in minimizing costs for the near-term planning horizon, but because they often inform planning strategies for these communities, they're interested in minimizing future costs under projected growth and climate change scenarios. We're looking at a much wider range of management options here, including land conservation, stormwater BMPs, buffers, repair of infrastructure leaks, upgrades in wastewater treatment, water conservation, as well as aquifer storage and recovery. We also have a wider range of constraints and goals that we're looking at here, both targets for total phosphorus and total nitrogen load reductions to protect both lakes in the downstream estuary, as well as sustainable water supply and maintaining minimum low flows for fish and land conservation goals. People are always interested in where the data come from these case studies, so I'll walk you through those sources for this example. In this case, although there were HSPF models available for the region, they had only been run for hydrology, not water quality, so we ran the SWIM model to provide runoff recharge and nitrogen and phosphorus loadings. We defined the hydrologic response units as a combination of land use and superficial geology using data from MassGIS. Water demand and withdrawal data came from annual reports that are submitted to the state of Massachusetts by the towns. We needed information on what portions of the watershed were covered by septic versus sewer systems. We derived these from utility maps and a state of Massachusetts database. Information on point source discharges is available from EPA's Discharge Monitoring Report database, which is available online and has data nationwide. And then finally, some of the more local infrastructure information had to be obtained from the town and utility data. We were also interested in looking at varying efficiencies for forested buffers as one management option. WMOST is designed to analyze up to 3 different relative load groups for riparian buffers. So if you think about a riparian buffer that's downstream from predominantly forest subwatershed, isn't going to be doing much in the way of load reduction as compared to a riparian buffer that's down gradient from an agricultural field. We used another tool called the Riparian Analysis Toolbox, which had been developed with support from the Chesapeake Bay program, and that allows you to rank riparian segments by the upgradient load received to determine the relative loads group. So if we zoom into this middle portion here, you can see that the riparian segments along the water body have been classified into conservation segments in black and restoration segments in green, 2 examples down here. And the tool is basically calculating what's draining to each of these segments. That allows you to rank those segments and define the relative load groups. You can do that by breaks and slope, changing the magnitude, a number of different break points. Again, we were interested to start out with looking at which stormwater BMPs are most cost-effective for reducing total nitrogen and total phosphorus loads. Here we compared 9 different stormwater BMPs starting out with a 2-inch design depth. And here, infiltration basins were consistently chosen as the only most cost-effective option. We were also interested in looking at different size BMP features and compared a 2-inch, 1-inch, and 0.6-inch design depth sizes. And here the 0.6-inch design depth was consistently chosen as the most cost-effective solution. This is partly because if you look at the distribution of precipitation events, magnitude in New England, a large proportion of these are relatively low magnitude events, much less than 1 inch, and a lot of the pollutants are coming off in the first flush. So if you have many small BMPs, you're capturing and treating those loads effectively. This is a graph showing results for 2005 optimization, looking at total phosphorus to a downstream lake. Baseline conditions are shown in the dark blue. Optimization results are shown in the light blue. And basically we found that a combination of maximum riparian buffer restoration in addition to some infiltration basins could meet the growing season loading target at a much reduced cost for the wet year as compared to infiltration basins alone. The results of this case study are being used to develop grant applications for improved watershed management using the results as supporting information. The case study is ongoing. We're just starting to use some growth projections provided by the Southeast Regional Planning and Economic Development District, along with some climate change scenarios to do some future scenarios, and these information will be used by them to inform communities in their development of master plans open space bands, and other strategic documents. So with that, we're ready for the second round of questions before we move on to multi-objective optimization.
All right, thank you, Amy and Naomi. We have a fair number of questions coming in, so we'll try to just dive in. The first one is, how did the Cabin John Creek project consider site constraints?
At this point, we have not, the preliminary runs did not consider additional site constraints. However, those can easily be factored in by changing the minimum and maximum areas available for BMP implementation. So this is an ongoing case study.
Okay. There's a lot of interest in understanding if there's any figures or information available for the level of effort for these two example projects that you've shown in terms of person hours or any other metric.
To be honest, we haven't quantified the hours spent, in part because we were running these case studies while developing and refining WMOST, so there was added time put into that iterative process. It can, depending on the complexity of the problem you're dealing with, it may take you a few weeks to gather the data needed.
Okay, kind of sounds like every other modeling project out there.
Right. But I should add that in any kind of long-range planning, you're going to need this kind of information anyway. So it's a kind of information that you need for long-range planning, and this is one mechanism for putting it all together in one place.
Okay. A lot of questions about what kind of support is provided for WMOST.
We'll get to some of the additional documentation at the end of the presentation. Basically, we have a comprehensive user guide, a theoretical documentation report which goes through all the equations. We do have recorded workshop training videos available online. This will be available as well. And later on in the webinar, we'll be asking if there is interest to set up a series of weekly training webinars where we go through things one module at a time, and I'll allow people time in between the sessions to populate their own case study and be working along with us in that part of that training process.
Okay, thanks. Could WMOST be used in a rural area to identify areas that should be conserved to avoid future water quality problems?
That's a good question, and in fact, that's one of the interests of the stakeholders in the Upper Taunton. That is, it's rapidly growing, and they're trying to identify areas that should be conserved and do that in the most cost-effective fashion.
Okay, and here's a question that we'll end on. I think it leads into the next section. I don't quite understand how the online optimization shown works. Is there a copy of the code or some literature related to the NEOS website?
The user guide provides a link to the NEOS website, and there is copious documentation associated with that website that you can download from them. And we provide an abbreviated description of the algorithms within the user guide to get people started.
Okay. I think we're going to stop some questions right now and move on to the next section. Thank you, everyone, for sending in those questions. They're very helpful, and we will continue to process them as they come in. But let's get back to the presentation and know that we will have one more Q&A session at the end to go.
All right, thanks, Dino. So now I'll be talking about some upcoming features with WMOST. One of the developments that is currently underway is a version of WMOST that performs multi-objective optimization. So to explain what that means in contrast to the optimization that Naomi just showed us, here's a comparison chart. So with single objective optimization, like in version 3 of WMOST and versions 1 and 2, we have one objective function, like minimizing cost, and consequently one optimal solution exists with the lowest cost. However, with multi-objective optimization, we can have numerous objectives, like minimizing cost and maximizing efficiency, for instance. And because these objectives compete, we will have multiple solutions that reflect the trade-offs between these objectives. So for instance, if we were to plot each solution in terms of how much the solution costs and its percent efficiency, you can see how this set of solutions reflects the trade-offs between those two objectives. Or in other words, we can't decrease cost without also decreasing efficiency. The ideal point in this domain would be up here in the upper left-hand corner, but realistically, a solution with the lowest possible cost and the highest possible efficiency can't be achieved. So you might be thinking, why didn't the examples that with WMOST version 3 consider multiple goals? Well, they did, but in optimization terms, the only objective in those examples was to minimize cost, and we implemented the other goals as constraints. So if we solved a single objective problem without a constraint, it would just look like this. We would have, for this set of solutions, our least cost solution is $1,000. However, with a constraint added, like making sure the efficiency is above 85%, now our lowest cost solution is this one, $4,000. So this type of trade-off curve information that we saw before can be obtained and pieced together with single objective optimization, but it takes some time. So just to reiterate, with single objective optimization, the outcome or result is a single optimal solution, and the optimization can be conducted using gradient-based types of solvers like linear and nonlinear programs, mixed integer programs. With multiple objective optimization, the outcome is multiple what we call Pareto optimal solutions, and I'll define that in a little more detail in a future slide. And we use population-based methods such as evolutionary algorithms or particle swarms. So in this multi-objective version of WMOST, I use what's called a multi-objective evolutionary algorithm, or MOEA. And generally speaking, MOEAs link with a simulation model and are used to generate an optimal population or set of solutions. So if we start with some input population of candidate solutions, candidate meaning that the solution is being considered but isn't necessarily optimal, each one of these solutions is comprised of different decision variables. If you recall back to the example at the beginning, these are just parameter values that represent an answer to your design problem. So each one of these solutions or set of decision variables is input into a simulation model. And for instance, for us, that's some watershed model, and that's going to allow us to determine how well these solutions perform using, by calculating objective function values associated with each solution. So in the context of integrated water resources management, this could be the cost of implementing the solution or the amount of nutrient removal it achieves, for instance. So this information is then provided to the evolutionary algorithm, which retains the strongest or fittest solutions, those with the best performance in their objective functions. And then this process continues with the new generation of solutions. So you can see some links to the analogy with evolution here. So the ultimate purpose of this algorithm search is to find what we call the set of Pareto optimal solutions. And to explain what this means, if we consider an example two-objective problem, optimization problem, where we want to minimize costs while maximizing reductions in runoff, the best possible solutions would have objective function values corresponding to this blue star, the lowest cost and the most reduction in runoff. And so here are some candidate solutions represented by the blue points, plotted in terms of their objective function values. So these solutions progress towards that ideal point during the search, and eventually we end up with a set of Pareto optimal solutions because we can't improve their performance any further. So in this WMOST work, I connect an evolutionary algorithm, this algorithm is known as BORG, with some watershed and green infrastructure models, the same models that are associated with version 3 of WMOST that Naomi just talked about. And I utilize all the same information that she showed you, which is provided by the user in that WMOST Excel user interface, and I bring this information into this version of WMOST, this multi-objective version, which is based in Python. So I'll demonstrate how we can use multi-objective optimization to address some of the issues experienced by the Taunton River watershed, same as the second case study Naomi described, which, if you recall, is undergoing rapid development and consequently experiencing adverse effects on their water quality and some water quantity issues as well. So in this multi-objective format of the case study, we can tackle multiple goals of the Taunton River watershed stakeholders simultaneously. So we want to minimize the capital and operation and maintenance costs. These represent our economic objectives while maximizing the reduction in runoff, which serves as a proxy for water quantity issues like flooding, and finally maximize reductions in nitrogen and phosphorus loads representing water quality issues. Now for the decision variables in this case study, focusing exclusively on implementing bioretention basin as a representative type of green infrastructure, unlike the work Naomi showed you where multiple types of green infrastructure were considered. The bioretention basin can be implemented on any of the impervious HRUs in the watershed. I'm showing these four impervious land use types here, and each of which has either sand and gravel soils or till and fine soils. So altogether we have 8 HRUs. And then another facet here is that you can implement either small capacity or large capacity bioretention basins on any one of those HRUs. So with the 8 HRUs and 2 choices per HRU, we have 16 total decision variables. All right, so now we'll take a look at the results of the optimization, the Pareto optimal solution. So here what we have is a 3-dimensional space where each of these 3 axes represents an objective. And recall that we want to minimize costs while maximizing reductions in runoff and nutrient loads. And I'm just showing the nitrogen loads here for simplicity. So the ideal solution in this domain would be in the lower left-hand corner, which can't be achieved, of course. So the shape of this surface is simply a result of the trade-off between the objectives. In general, as you spend more on green infrastructure, you increase the reductions in runoff and nutrient loads. Now, if I superimpose some slopes over these solutions, you'll notice that initial reductions in runoff and nutrient loads, where this orange dashed line is, come at a lower cost per unit reduction than over here where the red dotted line is. So there's a threshold in green infrastructure implementation where this change occurs. So in order to be able to understand where that threshold exists and just more generally understand the amounts and locations of green infrastructure that correspond to each of these solutions, so I'm going to first replot these same points in a 2-dimensional space, where now the reduction objectives are on the X and Y axes, and the cost is shown in color. So in this case, the ideal point is now in the upper right-hand corner, and it would be blue, lowest cost. So now to break down the amounts and locations of green infrastructure that are represented by each of these solutions, we'll start by considering one example solution and look at its characteristics or its decision variables using what's called a parallel plot. So the parallel plot tells us how much small capacity and large capacity bioretention basin is implemented, and note that the small capacity basin is less expensive. And then we'll add land use types to the plot, which range from least expensive to most expensive, and we'll add soil types at the top here that are alternating, such that each column now represents a different HRU, a different combination of land use and soil. So now we can show the decision variable values for this turquoise solution that I've circled over on the left using a line, or rather two lines. So for instance, this turquoise solution implements 40 acres of small capacity bioretention basin on an HRU with open non-residential land use type and sand and gravelly soils. And you can track that line across the screen for each of the HRUs for both the small capacity and large capacity bioretention basin, and this is a way of synthesizing all the information represented by each one of those solutions. All right, so rather than examine each solution one by one, what I'll do now is group some solutions into categories, starting with these, what I'm calling low reduction solutions here. So now in the parallel plot, we have many lines that correspond to this cluster of solutions. And generally notice varying amounts of implementation of bioretention basin across the first 3 HRUs, but little to no implementation on the commercial HRU over here. And I want to point out the commercial HRU carries or contributes the highest pollutant loads to the runoff, but it is the most expensive to implement green infrastructure on. So moving into this middle cluster of moderate reduction solutions, we notice now we have more implementation on the commercial land use types than we did before. And what's also worth noting is that we don't see any solutions that implement only on the commercial HRU, which indicates that targeting the high pollutant loads of commercial HRU is not an effective strategy. So this gives us our first sort of takeaway that implementing more bioretention basin on the HRUs contributing low nutrient loads is more cost effective than implementing fewer bioretention basins on the HRUs contributing high nutrient loads. All right, so finally in this last cluster of solutions that achieve high amounts of reduction, we notice lots of bioretention implementation across the board, but if we compare the small capacity and large capacity bioretention basins, there's definitely more implementation of the small capacity basin. You can see in the top figure. So because the majority of the pollutants are contained in the first flush, from a water quality standpoint, the increased volume of the bioretention basin isn't that advantageous relative to its cost. So that is another takeaway. So finally, you may have noticed this pattern of more implementation on sand and gravel versus on the till and fines, as indicated by this alternating pattern of lines up and down. This is because the sand and gravel allows for faster infiltration from the bioretention basin into the subsurface, which essentially augments the capacity of the bioretention basin. All right, so all the results I've shown thus far are for some baseline climate conditions, but ideally we want to be able to understand how to best implement and manage green infrastructure under a variety of climate scenarios. So here we have a list of the general circulation models included in the IPCC's Heat 5 report. So those are on the left, and then in the plot in the middle, the predicted mean annual changes in temperature and precipitation from each of these models are shown. The number of each model is what's plotted on the figure, and then the blue points represent the model results that are run under a lower emission scenario, that RCP 4.5, and the red points represent results run under a higher emission scenario, RCP 8.5. So what we've done is we've selected 4 points to roughly bound the extremes of changes in temperature and precipitation that are reflected by this collection of models, thereby representing a range of possible future climate scenarios. And I'll refer to these scenarios by color using this icon here to jog your memory on which scenarios are wetter, which scenarios are warmer. And what I'll do now is conduct the same optimization that you saw before with each of these scenarios, so we can get a better understanding of how green infrastructure implementation could vary to account for uncertainty in future climates. All right, so here are the results of those optimizations. For each of the 4 scenarios, we have a set of Pareto solutions that are color-coded by scenario. So from this three-dimensional plot on the left, you'll notice that we have the same trade-offs we saw before between the objectives. And if we look at the solutions in two-dimensional space here, what I want to point out is that solutions corresponding to the wetter future climates, like those blue and lime green points, achieve greater runoff reduction per unit cost. If you were to draw a horizontal line across that two-dimensional plot, you'll notice that for the same cost, you achieve more runoff reduction in the wetter climate solution. So this is essentially just because the bioretention basin is put to use more often in a wetter climate, which means that the value of implementing green infrastructure is greater under future wetter times. So hopefully this gives you an idea of what this multi-objective version of WMOST is capable of. It provides the needs of understanding the trade-off between a variety of different management options all at once. So here are a few conclusions from the case study. To summarize, so implementing more green infrastructure on the HRUs contributing low nutrient loads is more cost-effective than implementing less green infrastructure on those high nutrient load HRUs. It's more effective to locate small capacity green infrastructure on faster draining soils. And finally, the wetter climate change scenarios achieve higher runoff reductions per unit cost because the green infrastructure is used more frequently. This is a good argument for investing in green infrastructure given the uncertainty in future climate. All right, so as Naomi mentioned in the last questions break, WMOST is freely available online for download, and there are a number of resources here to help you use WMOST. So there's documentation including a user guide with case study appendices, so you can look at case studies that have been done in the past. There's the preprocessor utility. This formats data from SWIM, SWOT, and HSTS models into the format that WMOST needs. You can select input data from the EPA's S-Durate data mapper online. We also have all three versions of WMOST available online. All right, and so more information on help for you to use WMOST, the fact sheet, user guide, recorded workshop videos that we did for version 2 of WMOST. You'll have this presentation available to you afterwards, and you can use these links here. Also worth mentioning is that we'll be conducting an in-person workshop at the International Environmental Modeling and Software Conference coming up this summer in Fort Collins, Colorado. And so here are those links for your reference later to the workshop training that we did on version 2 of WMOST. Many of these are the same as in version 3. And to reiterate the future directions we're taking with WMOST, we're working on robust decision-making tools, including a tool that allows you to compare output from WMOST across multiple climate change scenarios. We're also working on a co-benefits module, and I gave you a taste of the multi-objective optimization version of WMOST today. We're always looking to collaborate because case studies help us refine and improve WMOST. So especially as we move forward with this upcoming work, co-benefits, robust decision-making, and multi-objective optimization, we're interested in case studies to help us with those components. And as Naomi mentioned, if there is sufficient interest, we'll be setting up an online WMOST course so that stakeholders that are interested in applying WMOST to their case study can have some hands-on experience and support. All right, so here's our contact information, and thanks very much for listening.
All right, thank you, Amy and Naomi, for that great presentation. We have a whole bunch of questions, and I encourage folks to keep typing in more questions. Amy, you just answered probably 5 or 6 of them with those last couple slides. So kudos to you. But well, I'm just going to pause for a second and wait for people to write in some more questions. But note that at the bottom of your screen, you'll see several poll questions. We do look at these poll results carefully, and so we encourage you to fill out the polls, whether you'd like to hear more about specific models or applied usage of models or anything else. So please take a moment to fill those out, and then we'll take a couple more questions. Let's see. There was one that was about if WMOST is open source, and I believe you said yes. There was a question about if there were any published studies that have used WMOST, and I'm not sure if they mean peer-reviewed publications or not, but can you speak to the nature of what you've published so far on this model?
The case studies that we've worked with are available in EPA reports as appendices to the user guide. We will be also publishing the results of the ongoing case studies in the near future. Some of those will come out in proceedings papers from the conference this summer, as well as additional reports set up like tutorials to help guide people through examples. Excellent, great. There's a couple general questions and then there's some specific ones. Here's a general one. Can WMOST be used to model pathogens? We don't currently have pathogen processing incorporated in WMOST, unfortunately. Okay. A pretty specific question about why the commercial areas in one of Amy's plots have the highest pollutant loads. Is it tied to the volume of the runoff? Is urban stream syndrome taken into account, i.e. the scouring of stream banks in WMOST?
That's a good question. I think it's related to the almost entirely impervious area with the commercial land use type, whereas the other non-residential and residential land use types had some permeable components. So the proportion is just so much greater in the commercial land use that the buildup and wash-off coefficients associated with those land use types are really dominant relative to the other land use types.
Okay. Here's a question regarding the cost figures that you showed. Do they reflect life cycle costs, including inspections and maintenance? The costs do include both capital costs and annual operation and maintenance, yes. We don't necessarily include everything you would include in a life cycle assessment, but we do include both the maintenance and the capital upfront costs. Okay. I'm going to pause just for a second so we can get the contact information up. Again, we will not be able to get to all of the questions that people are sending, so I encourage you, if you would like to follow up, to email our speakers or Jason Gilday, who is usually running these webinars, and their emails are shown on the screen in case you do have follow-up questions. And I'll leave this information up for a while we ask a couple more of the questions that we have. One of them is, what is the current size of the WMOST user base? And unfortunately, we don't have a good way of tracking that, but I encourage people to let us know about their use of WMOST and the case studies they're developing.
We can't track who downloads WMOST. That provides us no information on how many people are using it.
Okay, that's fair. How do you handle, or how can you correct if a model input, like SWOT, for example, has error associated with it? I think that might be just the general, how do you manage the uncertainty from uncertainty transfer from one model to the next? We do have a calibration module within
WMOST, so you can do some additional adjustments. So for example, a model might have been calibrated for a larger region and doesn't work quite as well in a smaller subwatershed that you're interested in. So there's some parameters that you can modify within WMOST, like the groundwater recession coefficient. You could apply an adjustment factor to the loading time series. There are a few different options for essentially recalibrating the model based on observation data that you have available for your subwatershed of interest. You can also do sensitivity analyses with those parameters to see how they might change your outcome.
But generally speaking, the data that's going into WMOST, if you're not putting good data in, we're not going to make it better for you, basically. Or, you know what I mean? It's reliant, like any model, reliant on the quality of data that you're using.
That's an excellent point. I'm going to take another moment so everyone online can look at the certificate that's available. The link is here on the screen for you to click, or you can download it from the Files box in the lower right-hand corner of your screen. The bottom of the screen is our TMDL modeling website, which has all of the archived webinars, including this one, which will hopefully be up within the month. And so I'll leave it up here for a few minutes while we answer a few more questions. One of the questions wants to know when you will incorporate pathogens in the future. It seems like pathogens is a hot topic for a lot of people.
I'll let you know after we get a budget. I'm afraid it's budget dependent at this point.
Understood. Here's a question. I'm not sure if I understand it, but I'll just share it with you. Will some of your conclusions become rules of thumb?
It's possible. I think we would want to run more case studies with different settings before we turn the results into rules of thumb. Although certainly with the Maryland case study, the intent is to inform communities and watersheds in similar settings dealing with similar constraints.
Yeah. The takeaways that I provided in the multi-objective section were in essence rules of thumb for that region, and what we'll do is see if those hold true with other case studies. And so I think that's a good way to look at the usage of WMOST for broader applications.
Okay. Here's a question about if WMOST includes BOD or COD, or if there are any plans in the future to incorporate that.
Currently, we do not include oxygen demand, and again, I'm afraid it's budget dependent at this point.
Okay. And then there's a couple questions about the interface between WMOST and sustain, and specifically if sustain is being used for the BMPs in both stormwater and agriculture, or just the stormwater.
It's being used for the stormwater BMPs and some of the agricultural BMPs, but not all. And again, there's more detail in the user guide and theoretical documentation.
Okay. We're running a little low on our questions now. I'm going to advance the slide and just say thank you to Naomi and Amy once again for the excellent presentation. And I encourage everybody to please visit EPA's Water Modeling Workgroup webpage in the future for details about the next webinar, which we haven't scheduled yet. But a quick reminder that an archive of today's webinar will be posted on our Water Modeling Workgroup webpage, and the link is on your screen now. And actually, we're getting some more questions. And then, yeah, I'm just going to take a pause and go back to this question. What is the difference between WMOST 3 and current available tools such as WEAP, W-E-A-P?
Well, one big difference is that WEAP is not free, and in fact, it's my understanding that you have to pay for each additional case study that you perform with WWEAP. At least that was the case when I last looked at that. WEAP is has linkages to groundwater models, so it's a little more complex and involved than WMOST is. Other than that, they do have somewhat similar goals. I won't purport to be an expert on WEAP, so I may not be doing it justice, but those are my initial impressions.
Okay, I think that's fair. Well, that kind of wraps up all the questions that we have. And so at this time, I want to thank Naomi and Amy for their excellent presentation. And I encourage people to reach out if they have any further questions. And with that, we'll end the webinar. And thank you, everyone, for attending. Have a really wonderful day.